Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. Because what I'm about to share with you is going to completely change how you think about the planet we call home. And I mean completely. Picture this. Right now, as we speak, we have detailed maps of 100% of Mars. Every crater, every canyon, every rock formation on that distant red planet. We know it all. We've mapped the surface of Venus through its thick, toxic clouds. We've charted the far side of the moon with stunning precision. But here's what's going to blow your mind. We've only mapped 20% of our own ocean floor. 20%. Let that sink in for a second. We know more about the surface of alien worlds millions of miles away than we do about the bottom of the seas that cover 71% of our own planet. It's like living in a house for your entire life but never bothering to look in 80% of the rooms. Except these aren't just empty rooms. They're filled with wonders and mysteries that would make science fiction writers weep with envy. Now, I know what you're thinking. The ocean is deep, sure, but how deep can it really be? Well, imagine this. Take the tallest building you've ever seen. Maybe it's the Empire State Building. Maybe it's one of those gleaming skyscrapers that pierce the clouds in Dubai or New York. Now imagine taking that building and dropping it into the deepest part of our ocean, a place called the Mariana Trench. That building wouldn't just disappear beneath the waves. It would fall for miles. Miles and miles, tumbling through the darkness until it finally came to rest on the ocean floor, still more than a mile underwater. The Mariana Trench plunges down 36,000 feet below sea level. To put that in perspective, and this is where it gets truly mind-bending, if you were sitting at the bottom of that trench, the water pressure pressing down on you would be equivalent to having 50 jumbo jets stacked directly on top of your body. 50 jumbo jets. But here's the crazy part. We've been down there. Humans have actually made that impossible journey to the deepest point on Earth. And what we found there changed everything we thought we knew about life itself. Yet for all our technological prowess, for all our satellites and supercomputers and space stations, we're essentially flying blind over most of our own planet. It's like being a detective trying to solve a case when 80% of the evidence is locked away in rooms you've never even opened. And the ocean is hiding some absolutely incredible secrets. In 1996, scientists made a discovery that sounds like something out of a fantasy novel. They were studying the waters between Iceland and Greenland when they stumbled across something that shouldn't exist, an underwater waterfall. Not just any waterfall, mind you. This cascade of water plunging through the depths carries 175 million cubic feet of water every single second. Think about that for a moment. You know Niagara Falls, right? That thundering, awe-inspiring torrent that draws millions of visitors every year? This underwater waterfall makes Niagara look like water dripping from a kitchen faucet. It's 3,500 times more powerful than Niagara Falls. 3,500 times. But you can't see it from the surface. It's completely invisible, hidden beneath the waves. This massive force of nature that dwarfs one of the most famous landmarks on Earth. It exists in a world we've barely begun to explore. Here's another mind-bender. We know more about the dark side of the moon, that mysterious face that never turns toward Earth, than we do about the darkness that lies beneath our own waves. Think about that irony. We've sent spacecraft hurtling through the vacuum of space to photograph and map lunar craters, but the deepest parts of our own oceans remain as alien and unexplored as distant galaxies. The ocean floor is scattered with 3 million shipwrecks. 3 million. Each one a time capsule, a frozen moment in history, lying in the eternal darkness. And here's what'll really get you. The combined value of all the treasure, cargo, and historical artifacts in those shipwrecks is estimated at $3 trillion. That's trillion with a T. More wealth than the GDP of most countries, just sitting there in the abyss, waiting to be discovered. But it's not just about treasure. Every one of those wrecks tells a story. Stories of exploration and adventure, of triumph and tragedy, of human courage and folly. They're archaeological sites that could rewrite our understanding of trade routes, naval warfare, and maritime technology. And we don't even know where most of them are. The scale of what we don't know is staggering. Imagine if someone told you that 80% of the land on Earth was still unmapped, that there were continents out there we'd never fully explored, mountain ranges we'd never climbed, forests we'd never walked through. You'd think they were crazy, right? But that's exactly the situation we're in with our oceans. And it's not like the ocean is just empty space down there. Oh no. The seafloor is home to mountain ranges that make the Himalayas look like speed bumps. There are underwater volcanoes that could swallow entire cities. There are trenches so deep that if you dropped Mount Everest into them, the peak would still be over a mile underwater. Scientists estimate that we've discovered less than 5% of all the species that live in our oceans. 5%. That means there are entire ecosystems down there, complete with predators and prey, food chains, and evolutionary adaptations that we've never even glimpsed. It's like having a library where you've only read 5 books out of every 100, and you're trying to understand the complete story of life on Earth. Some of these undiscovered creatures probably defy everything we think we know about biology. In the deepest parts of the ocean, where sunlight has never penetrated and the pressure would crush a human instantly, life has found a way to thrive. We've already found bacteria that eat methane, creatures that generate their own light, and ecosystems that exist completely independent of the sun's energy. What else is down there? What other impossible forms of life are thriving in conditions that would kill every land-dwelling creature in seconds? The ocean floor itself is a geological wonderland that we're only just beginning to understand. There are underwater rivers that flow for hundreds of miles, carved into the seafloor like the Grand Canyon. There are underwater lakes, actual lakes sitting on the bottom of the ocean, filled with water so dense and salty that it doesn't mix with the seawater above it. Submarines can literally float on these brine pools like boats on a regular lake. And here's something that'll make you pause your next beach vacation and stare out at the waves with new respect. The ocean floor is constantly changing. It's not just a static landscape sitting there in the dark. New mountains are being born from volcanic activity. Tectonic plates are shifting and colliding, creating new trenches and raising new ridges. Entire underwater landscapes are being reshaped by forces so powerful they make our earthquakes look gentle. Yet we're racing across the surface of this dynamic, living world in ships and planes, completely oblivious to the drama unfolding beneath us. It's like driving across a continent at night with your headlights off, catching only the occasional glimpse of what's really out there. The implications of our ignorance are staggering. Weather patterns, climate systems, ocean currents that affect every living thing on the planet are all influenced by underwater topography. We haven't mapped. We're trying to predict hurricanes and tsunamis and climate change while flying blind over 71% of our planet's surface. But here's what gives me chills in the best possible way. We're on the verge of changing all of that. Right now, as we speak, there's a revolution happening in ocean exploration. New technologies are emerging that will map the ocean floor faster and more accurately than ever before. Autonomous underwater vehicles are diving to depths that would kill human explorers, spending months at a time in the abyss, methodically charting every ridge and valley. Artificial intelligence is processing sonar data at speeds that would have seemed impossible just a few years ago. Satellites are detecting underwater mountains by measuring tiny changes in the ocean's surface that are invisible to the human eye. Crowdsourced mapping projects are turning every fishing boat and research vessel into an explorer, contributing millions of depth measurements as they go about their normal business. We're living through what might be the last great age of exploration on Earth. And unlike the explorers of centuries past who risked their lives crossing uncharted seas and unknown continents, We're exploring with robots and algorithms and technologies that can reveal secrets hidden for millions of years. But the clock is ticking. Climate change is altering ocean temperatures and currents, even as we race to map them. Coral reefs that have existed for thousands of years are dying before we can fully understand them. Deep-sea ecosystems that evolved over millions of years are being disrupted by pollution and warming waters. We're in a race to know our own planet before it changes beyond recognition. And that's exactly where our story begins, with humanity's most ambitious mapping project ever attempted, a quest to chart every square mile of the ocean floor by the year 2030. It's a goal that sounds impossible, but the people pursuing it believe it's not just possible, it's essential for our survival. Because once we complete this map, once we finally know our own planet completely, everything changes. Weather prediction becomes incredibly accurate. Tsunami warnings become precise down to individual beaches. New sources of energy and minerals become accessible. Archaeological discoveries could rewrite human history. And we finally understand what it means to live on a water planet spinning through the cosmos. The age of the unknown ocean is coming to an end, and what we're about to discover is going to reshape everything we thought we knew about Earth, about life, and about our place in the universe. Are you ready to dive in? To understand how we got to this incredible moment in ocean exploration, we need to go back, way back, because the story of humanity's relationship with the deep ocean is one of the most fascinating tales of fear, courage, and scientific breakthrough you'll ever hear. Picture yourself 3,000 years ago, standing on the deck of a Phoenician trading vessel. You're one of the greatest seafaring people in human history, masters of navigation and maritime trade. But even you, brave as you are, believe that somewhere out there in the vast blue expanse, the ocean simply ends. The Phoenicians were convinced that if you sailed far enough west, you'd hit a wall of impenetrable fog where ships would vanish forever, swallowed by the edge of the world itself. It wasn't just superstition, it was the best scientific understanding of the time. The ocean was finite, bordered by mystery and certain death. For thousands of years, this was humanity's relationship with the sea. We hugged coastlines like frightened children clinging to their parents. We ventured out just far enough to fish and trade, but the deep ocean, that belonged to sea monsters and demons, to Poseidon's wrath and the gods' fury. Ancient maps were filled with warnings. Here be dragons. Beyond, and this point, no ship returns. The ocean wasn't just unknown, it was unknowable, a realm where human knowledge simply couldn't penetrate. Then came 1492, and everything changed. Christopher Columbus wasn't just brave, he was either brilliantly visionary or completely insane, depending on how you look at it. His crew certainly thought he was insane. As they sailed further and further from any known land, watching the familiar coastlines disappear behind them, panic began to set in. Here's what's incredible about that voyage. Columbus's sailors weren't just worried about running out of food or getting lost. They genuinely believed they were sailing toward the edge of existence. They thought that any moment their ship would plunge off the world like water over a waterfall, tumbling into an infinite void. The crew came this close to mutiny. Can you imagine the conversations happening below deck? Grown men, experienced sailors, pleading with each other to turn back before they all died horribly at the world's edge. They weren't cowards. They were rational people operating with the best information they had. But Columbus kept pushing west, and when land finally appeared on the horizon, it wasn't just a new continent they'd discovered, it was a new understanding of what our planet actually was. The ocean didn't end in fog and monsters. It was vast beyond imagination, but it was real, it was navigable, and it connected distant shores in ways no one had ever dreamed. That single voyage shattered humanity's understanding of the world's oceans. But here's the thing. It only dealt with the surface. For the next 4 centuries, We got really good at sailing across the top of the ocean. We mapped coastlines, established trade routes, fought naval battles. We learned to read winds and currents and stars. But the ocean floor, that remained as mysterious as it had been to the Phoenicians. Ships would drop weighted ropes over the side, hoping to touch bottom. But in the deep ocean, they'd run out of rope long before they found the seafloor. It was like trying to measure the height of a skyscraper with a yardstick. Then, in 1872, everything changed again. HMS Challenger set sail from Portsmouth, England, on what would become the first systematic scientific exploration of the deep ocean. This wasn't a voyage of trade or conquest. It was pure scientific curiosity. The British Admiralty wanted to know what was really down there. Picture this ship, 340 feet long, carrying a crew of 243 scientists, sailors and officers. They loaded it with equipment that had never been used before: deep-sea thermometers, water sampling bottles, and miles upon miles of rope. Their mission was simple in concept but staggering in scope: circle the entire globe, stopping every few hundred miles to measure the depth and collect samples from the ocean floor. The Challenger expedition lasted 3.5 years. 3.5 years of sailing through storms and calms, dropping weighted lines into the abyss, hauling up bucket after bucket of mud and rock and strange creatures from depths no human had ever imagined. By the time they returned to England, they had travelled 68,700 miles and collected 492 depth measurements. 492. That's it. After 3.5 years of backbreaking work, sailing around the entire planet, they had managed to take depth measurements at fewer than 500 spots. But those measurements changed everything. For the first time in human history, we began to understand the true scale of the ocean's depths. The deepest measurement they took was 26,850 feet, deeper than Mount Everest is tall. They discovered underwater mountain ranges, deep trenches, and a seafloor topography as varied and dramatic as any landscape on land. The data from the Challenger expedition kept scientists busy for decades. They published 50 volumes of results, 50 volumes, describing new species, new geological formations, a new understanding of how our planet actually worked. But there was still a fundamental problem. Even after all that heroic effort, even after sailing around the world and dropping ropes into the abyss hundreds of times, they had measured less than 1,000% of the ocean floor. It would be like trying to map the entire United States by taking measurements at 5 random spots and trying to guess what lay between them. You might figure out that there were mountains and valleys somewhere, but you'd have no idea where they were, or how big they were, or what they looked like. That's where sonar changed everything. The breakthrough came in 1925 aboard a German research vessel called the Meteor. Instead of dropping ropes and weights, they started bouncing sound waves off the ocean floor. Sound travels through water at a predictable speed, about 4,800 feet per second. So, if you send a sound pulse straight down and measure how long it takes to echo back up, you can calculate exactly how deep the water is. It sounds simple now, but at the time, it was revolutionary. Instead of spending hours lowering and raising weighted ropes, they could take a depth measurement in seconds. Instead of getting 1 measurement per day, they could get thousands. The Meteor spent 2 years in the South Atlantic, crisscrossing the ocean basin and taking depth measurements every few miles. By the time they were done, they had completely redrawn the map of the Atlantic Ocean floor. They discovered that the ocean wasn't just a giant bathtub with a flat bottom. It was filled with underwater mountain ranges, deep valleys, and complex geological features that rivaled anything on land. But even sonar had its limitations. Early sonar systems could only measure straight down from the ship. Imagine trying to map a mountain range by driving down a single highway through it. You'd get some idea of the heights and valleys along your route, but you'd miss entire peaks and canyons just a few miles to either side. Still, progress was accelerating. By the 1950s, we had a rough understanding of the major features of the ocean floor. We knew about the Mid-Atlantic Ridge, the great underwater mountain range that runs down the center of the Atlantic Ocean. We had mapped some of the deepest trenches and identified the locations of underwater volcanoes, but we still hadn't been there. That changed on January 23, 1960, when two men climbed into what was essentially a steel ball and decided to visit the deepest place on Earth. Don Walsh was a United States Navy lieutenant. Jacques Piccard was a Swiss engineer and explorer. Together, they squeezed into a bathyscaphe called Trieste, a vessel that looked like a submarine designed by someone who had never seen a submarine before. It was basically a giant gasoline-filled float attached to a steel sphere about 6 feet in diameter. Their destination was Challenger Deep, the deepest known point in the Mariana Trench. The plan was simple: sink like a stone to the bottom of the ocean, take a look around, and somehow make it back to the surface alive. Here's what makes their dive absolutely insane. At about 30,000 feet down, 35,800 feet from the surface, they heard a loud crack. One of the small windows on their steel sphere had cracked under the enormous pressure. Now, picture this scenario. You're 6 miles underwater, deeper than any human has ever gone before. The water pressure outside your tiny steel ball is crushing, over 16,000 pounds per square inch, and you hear the sound of something breaking. Any rational person would have said, "That's it, we're going back up. This is insane." But Walsh and Piccard kept going. They descended another 800 feet to the very bottom of Challenger Deep, becoming the first humans to visit the deepest place on Earth. The pressure at that depth was so intense that it was like having 1,000 tons pressing down on every square foot of their vessel. And you know what they found down there? Life. Even at that crushing depth, even in the eternal darkness where no sunlight had ever penetrated, they saw fish swimming past their porthole. Flatfish, moving slowly across the seafloor like alien creatures in an alien world. It was proof that life could exist literally anywhere on our planet. If creatures could thrive at the bottom of the deepest trench, under pressure that would instantly crush any land animal, then life was far more resilient and adaptable than anyone had imagined. The Trieste dive lasted 9 hours, to 9 hours in a steel ball barely large enough for 2 people, sitting on the bottom of the deepest ocean trench on Earth. When they finally surfaced, they had pushed human exploration to its absolute limit. But even that incredible achievement gave us just one tiny glimpse of the deep ocean. It was like sending explorers to stand on a single spot on the moon for a few minutes, and then trying to understand what the entire lunar surface was like. By the 1960s, we had taken thousands of sonar measurements and achieved the ultimate deep-sea dive, but we had still mapped less than 5% of the ocean floor with any real detail. We knew there were mountains and valleys and trenches down there, but we didn't know where most of them were or what they looked like. The ocean remained largely unknown, a vast frontier that covered most of our planet, but might as well have been on another world entirely. What we needed was a revolution in mapping technology. We needed ways to see the ocean floor clearly, quickly, and accurately. We needed to turn the mysterious abyss into something we could understand and explore systematically. That revolution was coming. But first, we had to develop technologies that could match the ocean's incredible scale and complexity. We needed tools that could map underwater mountain ranges, the size of continents, and capture details smaller than a house, all while working in an environment that would destroy most human-made equipment in seconds. The stage was set for the greatest mapping project in human history. And that revolution? It's happening right now, as we speak, and it's absolutely mind-blowing. Remember those early sonar systems that could only measure straight down? Well, imagine if instead of dropping a single fishing line into a lake, you could cast an entire net that would tell you the depth at hundreds of points simultaneously. That's exactly what modern multi-beam sonar systems do. These incredible machines fire 256 separate sound beams at once, spreading out in a fan pattern beneath the ship. Instead of getting one depth measurement every few seconds, they're painting a detailed picture of the seafloor in real time, capturing every ridge, every valley, every boulder larger than a car. Picture this: a research vessel moving across the ocean surface at 15 knots, its sonar system sweeping back and forth like a lighthouse beam, except instead of light, it's using sound to illuminate the darkness below. Every ping reveals another strip of seafloor in stunning detail. Mountains that have been hidden for millions of years suddenly appear on computer screens in full three-dimensional glory. But here's where it gets really wild. These aren't just simple depth measurements anymore. Modern sonar can tell you what the seafloor is made of. Rocky, sandy, muddy, covered in coral. The sound waves bounce back differently depending on what they hit, and computers can analyze those differences to create maps that show not just the shape of the ocean floor, but its composition. It's like having X-ray vision for the entire ocean. And we're not stopping there. Meet the autonomous underwater vehicles, AUVs, that are revolutionizing deep-sea exploration. These are robots that can dive to depths that would crush human explorers, stay underwater for months at a time, and map the seafloor with precision that would make a Swiss watchmaker jealous. Take Boaty McBoatface, DZA. Yes, that's really its name, and yes, it came from an internet poll that got slightly out of hand. But don't let the silly name fool you. This yellow torpedo-shaped robot is a technological marvel. It can dive to depths of 20,000 feet, travel 1,500 miles on a single mission, and operate completely independently for 6 months straight. Think about that for a second. 6 months. Underwater. Alone. While we're up here going about our daily lives, Boaty is down there in the eternal darkness, methodically mapping every square foot of seafloor it encounters. It's equipped with sonar systems, cameras, and sensors that can detect everything from water temperature to chemical composition. It's like having a tireless, fearless scientist who never needs to eat, sleep, or come up for air. And Boaty isn't alone. There are dozens of these underwater robots working around the clock, covering more ocean floor in a single month than human explorers mapped in the entire 19th century. But the real game changer? Satellites. Now, I know what you're thinking. How can satellites map the ocean floor? They're in space, and the ocean is, well, underwater. It seems impossible, right? Here's where physics gets absolutely beautiful. Water is heavy, really heavy. And when there's an underwater mountain 3,000 feet tall sitting on the ocean floor, all that rock and metal creates a tiny gravitational pull. That gravitational pull actually tugs on the water above it, creating a bulge on the ocean surface. We're talking about incredibly small bulges here. A mountain 3,000 feet tall creates a bulge of just 3 feet on the surface. 3 feet spread across miles and miles of ocean. It's so subtle that you could sail right over it and never notice. But satellites notice everything. Modern radar satellites can measure the height of the ocean surface to within inches. They're circling the Earth, bouncing radar beams off the waves, and detecting gravitational bulges so small they're practically invisible. Then, computers analyze all that data and work backwards. If there's a bulge here, there must be a mountain down there. If there's a depression there, there must be a trench. It's like being able to see through the ocean by watching the tiny ways it warps and bends on the surface. This satellite technology has already revealed underwater mountain ranges the size of Europe that we never knew existed. Entire oceanic features larger than most countries, just sitting there waiting to be discovered. But even satellites and sonar and underwater robots weren't enough to tackle the sheer scale of mapping the entire ocean floor. We needed something more. We needed artificial intelligence. Here's the problem. Modern mapping expeditions generate absolutely staggering amounts of data. A single research vessel, equipped with multi-beam sonar, can collect more information in one day than human scientists could analyze in a year. We were drowning in data. Enter AI. Machine learning algorithms can now process sonar data at speeds that seem almost magical. What used to take a team of scientists months to analyze, AI can handle in hours. These systems can identify underwater features, classify different types of seafloor, and even predict where interesting geological formations might be located. And they're getting smarter every day. AI systems are learning to recognize patterns that human scientists miss. They can spot the subtle signatures of underwater volcanoes, identify areas where rare minerals might be concentrated, and even predict where new hydrothermal vents might be forming. But perhaps the most brilliant innovation is something called crowdsourced bathymetry. Remember how the Challenger expedition managed to take 492 depth measurements in 3.5 years? Well, we've figured out how to turn every ship on the ocean into a mapping vessel. Commercial fishing boats, cargo ships, research vessels, even private yachts, they're all equipped with basic depth-finding sonar for navigation. Instead of keeping that data to themselves, they're sharing it with a global database that's building the most comprehensive map of the ocean floor in human history. A fishing boat heading out for a routine day of work contributes dozens of depth measurements. A cargo ship crossing the Pacific adds thousands of data points to areas that have never been properly mapped. A yacht sailing around the Caribbean fills in gaps in our knowledge that have existed for centuries. It's like having millions of explorers working simultaneously, each contributing tiny pieces to a vast puzzle. The numbers are staggering. Every month, this crowdsourced effort adds millions of new depth measurements to our global ocean database. In just the past 5 years, fishing vessels and merchant ships have contributed more mapping data than all the scientific expeditions of the previous century combined, and the technology keeps getting better. New sonar systems are being developed that can map 40 times faster than current equipment. Underwater robots are being designed that can operate at depths and pressures that would destroy today's vehicles. Artificial intelligence systems are learning to interpret sonar data with superhuman accuracy. We're not just mapping the ocean anymore, we're developing a complete understanding of it. But speed isn't the only factor driving this revolution. We're also achieving unprecedented accuracy. Modern mapping systems can detect features as small as a few feet across, even in water miles deep. We can map individual boulders on the seafloor, chart the exact boundaries of coral reefs, and identify shipwrecks with photographic clarity. Think about what this means. We're creating maps of the ocean floor that are more detailed than most maps of dry land. We're achieving resolution so high that future ocean explorers will be able to navigate underwater terrain as easily as we drive through familiar neighborhoods. And it's happening fast, really fast. Just 20 years ago, we had mapped less than 10% of the ocean floor with any meaningful detail. Today, we're approaching 30%. At our current rate of progress, we'll have rough maps of the entire ocean by 2030, less than 5 years from now. But rough maps isn't good enough anymore. The goal now is complete, high-resolution mapping of every square mile of seafloor on the planet. We want to know every underwater mountain, every deep-sea valley, every coral reef, every shipwreck. We want to know our own planet as well as we know Mars. The tools to achieve this goal already exist. Multi-beam sonar systems that can map vast areas in a single pass. Autonomous underwater vehicles that never tire and never need to surface. Satellites that can detect underwater features from space. Artificial intelligence that can process data faster than any human team. What we need now is scale. More ships, more robots, more satellites, more computing power. And that's exactly what we're getting. Major oceanographic institutions around the world are expanding their fleets. Technology companies are investing billions in underwater robotics. Space agencies are launching new satellites specifically designed for ocean mapping. Artificial intelligence systems are becoming more sophisticated every month. The convergence of all these technologies is creating a perfect storm of discovery. We're not just incrementally improving our knowledge of the ocean, we're on the verge of a complete revolution in how we understand our planet. But here's what really gives me chills. This isn't just about satisfying scientific curiosity. Complete ocean mapping will transform weather prediction, climate science, disaster preparedness, resource exploration, and our understanding of life itself. And we're so close, closer than most people realize. The race is on to map every corner of the ocean before climate change alters what we're trying to map. It's a race against time, against rising seas and warming waters and changing currents. But it's a race we're going to win. And you want to know why I'm so confident we're going to win this race? Because of what we've already discovered. The wonders that have emerged from just mapping 30% of the ocean floor are so incredible, so mind-bending, that they've completely rewritten our understanding of what Earth is really like. Let me take you on a journey to some of the most amazing places on our planet. Places that exist in the eternal darkness of the deep ocean. Places that until recently were more mysterious than the surface of Mars. First stop, the Mid-Atlantic Ridge. Picture the longest mountain range on Earth. Not the Andes, which stretch 4,300 miles down the spine of South America. Not the Rockies, which extend 3,000 miles across North America. Not even the Himalayas, home to the world's tallest peaks. The Mid-Atlantic Ridge stretches 10,000 miles from the Arctic Ocean to the tip of Africa. 10,000 miles of underwater mountains, rising from the abyssal depths like a massive spine running down the center of the Atlantic Ocean. But here's what makes this mountain range truly extraordinary. It's not just sitting there, it's growing. The Mid-Atlantic Ridge is where two massive tectonic plates meet, slowly pulling apart and creating new ocean floor. Every year, the Atlantic Ocean gets about an inch wider as molten rock from deep within the Earth rises up through cracks in the seafloor and solidifies into new mountainous terrain. We're talking about a mountain range that's actively building itself, year after year, century after century. The peaks we see today didn't exist when Columbus sailed across the Atlantic. The valleys and ridges that define this underwater landscape are younger than human civilization. And it's not just one continuous ridge either. The Mid-Atlantic Ridge is a complex system of peaks and valleys, underwater canyons and volcanic vents, stretching longer than the distance from New York to Los Angeles, twice. When researchers first mapped the full extent of the Mid-Atlantic Ridge in the 1960s, they realized they were looking at one of the most geologically active places on Earth. This wasn't just an underwater mountain range, it was a window into the very forces that shape our planet. But the Mid-Atlantic Ridge is just one example of the incredible underwater topography we've discovered. Let's dive deeper. Literally deeper. Welcome to the Puerto Rico Trench, where the ocean floor plunges to depths that make the Grand Canyon look like a shallow ditch. At its deepest point, the Puerto Rico Trench drops 28,231 feet below sea level. That's more than 5 miles straight down. To put that in perspective, if you could drain all the water from this trench and hike from the rim to the bottom, it would take you hours of continuous walking just to reach the deepest point. You'd be hiking through an underwater landscape more dramatic than anything found on dry land. But here's what's truly incredible about the Puerto Rico Trench. It's full of life. Scientists exploring the deepest parts of this trench have discovered creatures that shouldn't be able to exist. Amphipods, tiny shrimp-like creatures thriving at pressures that would crush a military submarine like a tin can. These aren't just any amphipods either. They're specially proof, adapted for life in the crushing depths, with bodies that can withstand pressure 1,600 times greater than what we experience at sea level. Some of them are translucent, like living glass sculptures floating through the eternal darkness. Others have developed bioluminescence, creating their own light in a world where sunlight has never penetrated. The existence of these creatures has revolutionized our understanding of life's limits. If complex organisms can thrive in the most extreme environment on Earth, under crushing pressure, in eternal darkness, in near-freezing temperatures, then life might be possible in places we never imagined. The moons of Jupiter and Saturn, for instance, with their subsurface oceans hidden beneath miles of ice. But the Puerto Rico Trench isn't the only place where we've found life thriving in impossible conditions. Let me tell you about one of the most mysterious discoveries in the history of ocean exploration, the Baltic Sea anomaly. Picture a disc-shaped object, 200 feet across, sitting on the bottom of the Baltic Sea. It's perfectly round, with what appear to be ramps leading up to its edges and a series of geometric patterns carved into its surface. When sonar first detected this object in 2011, the images were so clear and so geometrically precise that they looked like something out of a science fiction movie. The Baltic Sea anomaly doesn't look natural. It looks designed, manufactured, like a crashed spacecraft that somehow ended up on the ocean floor. Now, before you start thinking about little green men, let me tell you what scientists think it actually is. The most likely explanation is that it's a massive piece of glacial sediment deposited when ice sheets covered northern Europe thousands of years ago. The geometric patterns might be natural fractures in the rock, and the disc shape could be the result of ancient ice flows. But here's what makes the Baltic Sea anomaly so fascinating. Even if it's completely natural, it demonstrates just how alien our own ocean floor can appear. This object looks so artificial, so precisely engineered, that it fooled experienced sonar operators and marine geologists. It makes you wonder what other seemingly impossible features are sitting on the ocean floor, waiting to be discovered. Speaking of impossible features, let me blow your mind with something called brine pools. Imagine you're piloting a submarine through the depths of the Gulf of Mexico. You're cruising along at 3,000 feet below the surface when suddenly you encounter something that shouldn't exist. A lake. Not just any lake. A lake sitting on the bottom of the ocean. These brine pools are bodies of water so dense with salt and other minerals that they don't mix with the seawater above them. They have distinct shorelines, just like lakes on land. They have waves lapping at their edges, and they're so dense that your submarine would literally float on their surface like a boat on a regular lake. The water in these underwater lakes is typically 5 to 10 times saltier than normal seawater. It's so dense that anything that falls into it either floats on the surface or sinks much more slowly than it would in regular water. But here's the really wild part. These brine pools are toxic to most marine life. Fish that swim into them die almost instantly, their bodies preserved in the super salty water like specimens in formaldehyde. The edges of these underwater lakes are often littered with the remains of creatures that made the fatal mistake of swimming too deep. Yet even these toxic underwater lakes support life. Bacteria thrive in the super salty water, forming thick mats around the shorelines. Tube worms cluster at the edges, feeding on the bacteria. It's an entire ecosystem based on chemistry so extreme it would kill most ocean creatures instantly. These brine pools aren't rare, either. We've found hundreds of them in the Gulf of Mexico, the Mediterranean Sea, and the Red Sea. Each one is a chemical wonderland, a natural laboratory where evolution has created life forms adapted to conditions that exist nowhere else on Earth. But perhaps the most revolutionary discovery in the history of ocean exploration happened in 1977, when scientists first encountered hydrothermal vents. Picture this. You're in a submersible, exploring the depths of the Pacific Ocean near the Galapagos Islands. The water around you is near freezing, and you're in total darkness, miles from the nearest ray of sunlight. Suddenly, your lights illuminate something impossible. Jets of superheated water shooting out of the seafloor like underwater geysers. The water temperature at these vents reaches 600 degrees Fahrenheit, hot enough to melt lead. But that's not the impossible part. The impossible part is that these scalding underwater geysers are surrounded by some of the most abundant life on Earth. Giant tube worms, 8 feet long and thick as your arm, cluster around the vents like alien flowers. Ghostly white crabs scuttle across rocks, coated in bacterial mats. Strange fish swim through water hot enough to cook them, somehow thriving in conditions that would kill any surface-dwelling creature instantly. This was the discovery that changed everything we thought we knew about life. For billions of years, scientists believed that all life on Earth ultimately depended on the sun. Plants convert sunlight into energy through photosynthesis. Animals eat the plants or eat other animals that eat the plants, and so on up the food chain. Everything, ultimately, traced back to solar energy. But the hydrothermal vents proved that assumption wrong. The ecosystems around these underwater hot springs don't depend on sunlight at all. They're powered by chemosynthesis, i.e., bacteria that convert the chemical energy from the vents into food, just like plants convert solar energy into food through photosynthesis. It's an entirely parallel form of life, existing completely independently of the sun. The implications of this discovery are staggering. If life can thrive around hydrothermal vents on Earth, then it might be possible around similar features on other planets. The subsurface oceans of Europa and Enceladus, the moons of Jupiter and Saturn, might harbor their own hydrothermal vent ecosystems. We went from assuming that life required sunlight to discovering that life could exist in places we never imagined. Dark, crushing, superheated environments that are more like alien worlds than Earth. And we found hundreds of these hydrothermal vent fields scattered across the ocean floor. Each one is unique, supporting different species adapted to slightly different conditions. Some vents create towering mineral chimneys, called black smokers, that spew dark clouds of metallic particles. Others form fields of white, crystalline structures that look like underwater crystal gardens. These discoveries have revolutionized our understanding of evolution, adaptation, and the very definition of what makes a place habitable. But here's what gives me chills. All of these incredible discoveries, the Mid-Atlantic Ridge, the Puerto Rico Trench, the Baltic Sea anomaly, the brine pools, the hydrothermal vents, seafloor, they represent less than 30% of the ocean floor. 70% of our planet's seafloor remains unmapped and unexplored. If we've found wonders this incredible in just the portions we've surveyed, what's waiting for us in the vast areas we haven't even glimpsed yet? What alien landscapes are hidden in the deep Pacific? What impossible life forms are thriving in trenches we haven't discovered? What geological features are waiting to rewrite our understanding of how planets work? Every square mile we map reveals new surprises, new impossibilities, new forms of life and geological processes that challenge everything we thought we knew about Earth. And we're just getting started. Now imagine what happens when we finish the job, when we have complete high-resolution maps of every square mile of ocean floor on the planet. When the age of the unknown ocean finally comes to an end, the transformation will be absolutely staggering. Let's start with something that affects every single person on Earth: weather prediction. Right now, our best weather models are incredibly sophisticated, but they're working with incomplete information. They know the temperature of the ocean surface, the speed and direction of surface currents, and the basic topography of the major underwater features. But they don't know the detailed shape of the seafloor, and that detailed shape drives underwater currents that influence weather patterns around the globe. Here's how it works. Ocean currents aren't just surface phenomena. Deep underwater currents flow along the ocean floor like rivers, carrying warm and cold water across vast distances. These currents are shaped by underwater mountains, valleys, and ridges in ways that are incredibly complex and difficult to predict. When a deep current hits an underwater mountain, it can be deflected hundreds of miles off course. When it flows through an underwater valley, it can speed up or slow down dramatically. When warm and cold currents meet at specific underwater topographical features, They can create circulation patterns that influence weather thousands of miles away. But without detailed maps of the seafloor, weather prediction models have to guess at these interactions. Complete ocean mapping will change that forever. With perfect knowledge of seafloor topography, oceanographers will be able to model underwater currents with unprecedented accuracy. They'll know exactly how water flows through every underwater valley, around every seamount, through every ridge system. And when you can predict ocean currents with perfect accuracy, you can predict weather with 99% accuracy. Think about what that means. Hurricane forecasts that are correct not just about whether a storm will hit, but exactly where it will make landfall, down to individual beaches. Tornado warnings that can predict not just the general area where severe weather might develop, but the specific neighborhoods that need to evacuate. Farmers will know exactly when to plant and harvest their crops. Airlines will be able to route flights around turbulence days in advance. Cities will be able to prepare for floods and droughts with precision that seems almost magical today. But weather prediction is just the beginning. Complete ocean mapping will revolutionize tsunami warning systems in ways that will save millions of lives. Here's the terrifying reality of tsunamis. They're incredibly difficult to predict because they depend entirely on underwater topography. When an earthquake occurs on the seafloor, it sends shock waves racing across the ocean at the speed of a jet airplane. But the height and destructive power of the resulting tsunami depends on the exact shape of the seafloor between the earthquake and the coast. If those shock waves travel across a flat underwater plain, they might create a relatively small tsunami. But if they're channeled through underwater valleys or amplified by underwater ridges, they can create waves 100 feet tall or higher. Right now, tsunami warning systems have to make educated guesses about how underwater topography will affect wave propagation. They know the general features of the seafloor, but they don't have the detailed information needed to predict exactly how a tsunami will behave. Complete ocean mapping will give them that information. With perfect knowledge of seafloor topography, tsunami warning systems will be able to predict not just that a tsunami is coming, but exactly how high the waves will be when they reach each section of coastline. They'll be able to issue warnings that are specific down to individual beaches. Evacuate this area. Waves will be 20 feet high. This area is safe. Waves will be less than 3 feet. The difference between a general tsunami warning and a precise, location-specific warning is the difference between evacuating entire coastlines and evacuating only the areas that are actually in danger. It's the difference between saving thousands of lives and saving millions of lives. But the benefits of complete ocean mapping go far beyond disaster preparedness. Hidden beneath the waves are mineral resources that could transform our entire approach to renewable energy. The ocean floor is scattered with nodules of rare earth elements, AGC, materials that are essential for building wind turbines, solar panels, and electric car batteries. These nodules form over millions of years as minerals precipitate out of seawater and accumulate on the seafloor like underwater rocks. We've already found fields of these nodules in the deep Pacific that contain enough rare earth elements to build millions of wind turbines. But without detailed maps of the seafloor, we don't know where most of these mineral deposits are located. Complete ocean mapping will reveal the location of every significant mineral deposit on the planet. Imagine discovering enough rare earth elements to make renewable energy infrastructure essentially unlimited. Enough lithium for billions of electric car batteries. Enough rare earth metals for solar panels to power entire continents. These resources exist. They're sitting on the ocean floor right now, waiting to be discovered. We just don't know where most of them are. And it's not just about finding new resources, it's about optimizing the resources we're already using. Complete ocean mapping will revolutionize global shipping in ways that could cut carbon emissions by hundreds of millions of tons every year. Here's something most people don't realize. Ships don't just sail in straight lines across the ocean. They follow shipping routes that are optimized for safety, fuel efficiency, and travel time. But these routes were established decades or even centuries ago, based on limited knowledge of ocean currents and underwater topography. With complete knowledge of seafloor topography and the underwater currents it creates, shipping companies will be able to optimize their routes with unprecedented precision. They'll know exactly where to find favorable currents that can add several knots to their speed. They'll know how to avoid underwater features that create turbulence and rough seas. The fuel savings alone could be enormous. If global shipping becomes just 10% more efficient, that represents a reduction of 400 million tons of carbon emissions every year. That's equivalent to taking 80 million cars off the road. But perhaps the most exciting possibility is what complete ocean mapping might reveal about human history itself. During the last ice age, which ended about 12,000 years ago, sea levels were 400 feet lower than they are today. Vast areas of what is now ocean floor were dry land, supporting forests, rivers, and possibly human civilizations. When the ice sheets melted and sea levels rose, entire landscapes were flooded. Valleys became underwater canyons, hills became seamounts, and any evidence of human habitation was submerged beneath hundreds of feet of water. Complete ocean mapping could reveal archaeological sites that would rewrite human history. Imagine discovering the remains of cities that existed before the pyramids were built. Stone tools and pottery scattered across what were once fertile river valleys. Evidence of human migration routes that crossed land bridges, now buried beneath the waves. These archaeological treasures exist. They're sitting on the continental shelves around every continent, preserved in the cold, oxygen-poor environment of the deep sea. But without detailed maps, we don't know where to look for them. We might discover that human civilization is far older and more widespread than we currently believe. We might find evidence of technologies and cultures that existed before the flood that ended the Ice Age, erased them from the surface world. And here's what really gets me excited. Complete ocean mapping will reveal features and phenomena that we can't even imagine yet. Every time we've achieved a new level of detail in ocean mapping, we've discovered things that nobody predicted. Underwater waterfalls, brine pools, hydrothermal vent ecosystems, the Baltic Sea anomaly. What will we discover when we can see every boulder, every ridge, every valley on the ocean floor? What geological processes are happening down there that we've never observed? What forms of life are thriving in environments we haven't even discovered yet? What physical phenomena exist in the deep ocean that could revolutionize our understanding of chemistry, physics, and biology? The ocean covers 71% of our planet's surface. It contains 99% of our planet's habitable space, and we've explored less than 5% of it in any meaningful detail. Complete ocean mapping isn't just about filling in the blank spaces on our maps. It's about completing our understanding of what it means to live on a water planet. It's about finally knowing our home. But here's the thing that keeps ocean scientists awake at night. We're not just racing to map the ocean, we're racing against time itself. Because while we're working to understand our planet is changing beneath our feet, or in this case, beneath our waves. Let me tell you about one of the most ambitious and urgent scientific projects in human history, the race to map the entire ocean floor by 2030. It started with a phone call in 2017. The Nippon Foundation, a Japanese philanthropic organization, called up the world's leading ocean scientists with an offer that was impossible to refuse. $185 million to map the entire ocean floor in just 13 years. $185 million. For context, that's more money than most countries spend on their entire scientific research budgets in a year, and they wanted to spend it all on a single, seemingly impossible goal: complete the greatest mapping project in human history before the year 2030. Why 2030? Because that's when the United Nations wants to achieve sustainable management of ocean resources. You can't manage what you don't understand, and you can't understand what you haven't mapped. But there's another, more urgent reason for the deadline. Climate change is altering the ocean faster than we can study it. Ocean temperatures are rising, currents are shifting, sea levels are changing. Coral reefs that have existed for thousands of years are dying in just a few decades. We're in a race to map and understand marine ecosystems before they disappear forever. Leading this monumental effort is a man named Larry Meyer, and his story is absolutely incredible. Picture a scientist who has spent his entire career pushing the boundaries of what's possible in ocean mapping. Larry runs the Center for Coastal and Ocean Mapping at the University of New Hampshire, and he's developed sonar systems that can map the seafloor 40 times faster than anything that existed just a decade ago. 40 times faster. That's not incremental improvement, that's a revolution. But even with technology that advanced, even with the largest funding commitment in the history of oceanography, the math is staggering. The ocean covers 139 million square miles. To map it all by 2030, they need to survey about 350,000 square miles every single month. That's like mapping an area the size of Texas and California combined every 30 days for 13 straight years. To put that in perspective, the most productive ocean mapping expeditions in history have covered maybe 50,000 square miles in a year. Larry Meyer's team needs to be 7 times more productive than the best efforts in human history, and they need to sustain that pace for over a decade. It sounds impossible, doesn't it? But Larry has a secret weapon. Ocean Infinity. Ocean Infinity is a company that sounds like it came straight out of a science fiction novel. They've built a fleet of autonomous surface vessels that can map the ocean 24 hours a day, 7 days a week, without any human crew aboard. Think about that for a second. These are ships that sail themselves across the vast expanses of the ocean, deploying underwater robots, collecting sonar data, and communicating with satellites, all without a single person aboard. Each Ocean Infinity vessel is equipped with multiple autonomous underwater vehicles, APZ, those torpedo-shaped robots we talked about earlier. While the surface ship sails in a predetermined pattern, the underwater robots spread out like a pack of hunting wolves, each one mapping a different section of seafloor. When the robot's batteries run low, they surface automatically, dock with the mothership, recharge, download their data, and dive again. The entire operation is coordinated by artificial intelligence systems that can adapt to weather conditions, equipment failures, and unexpected discoveries. Ocean Infinity currently operates 8 of these vessels, and they're building more. Each one can map approximately 15,000 square miles of ocean floor per month, roughly the size of Switzerland. But even 8 ships isn't enough to meet the 2030 deadline. They need dozens more. They need a whole fleet of robotic explorers spreading across the world's oceans like a high-tech armada. And they're building that fleet as fast as they can. But here's what makes this race against time so urgent. While they're working to map the ocean, climate change is rapidly altering what they're trying to map. Take coral reefs, for example. These are some of the most biodiverse ecosystems on Earth, underwater rainforests that support millions of species. But rising ocean temperatures are causing massive coral bleaching events that can kill entire reef systems in just a few months. Scientists are in a desperate race to map and study these coral reefs before they disappear. They're using underwater robots equipped with high-resolution cameras to create detailed 3-dimensional models of reef systems, capturing every branch of coral, every fish species, every ecological relationship. But they're losing the race. The Great Barrier Reef, one of the natural wonders of the world, has experienced massive bleaching events in recent years. Entire sections that were vibrant and alive just a decade ago are now white graveyards of dead coral. Scientists are mapping these areas as fast as they can, but they're essentially creating a record of ecosystems that are dying even as they're being studied. It's heartbreaking and urgent and absolutely crucial, all at the same time. The same urgency applies to polar regions, where warming temperatures are changing the landscape faster than anywhere else on Earth. In the Arctic Ocean, sea ice that has existed for thousands of years is melting away, revealing seafloor that has been hidden beneath ice sheets for millennia. This is a once-in-a-civilization opportunity to map and study areas that have been inaccessible throughout human history. But it's also a rapidly closing window. As the Arctic continues to warm, these newly exposed areas are becoming accessible to commercial shipping, fishing, and resource extraction. Scientists have maybe a decade to study these pristine environments before they're transformed by human activity. Arctic mapping expeditions are working around the clock during the brief summer months when the ice retreats enough to allow access. They're deploying autonomous underwater vehicles beneath the remaining ice sheets, using them to map areas that no human has ever seen. But every year, the window gets smaller. Every summer, the race gets more urgent. The same pressure exists in Antarctica, where warming temperatures are causing massive ice shelves to collapse. When an ice shelf that's existed for thousands of years suddenly breaks away, it reveals seafloor that's been hidden in darkness for millennia. These are extraordinary opportunities for discovery, but they're also signs of a changing planet that scientists are struggling to keep up with. And it's not just about mapping new areas, it's about updating maps of areas we've already studied. Ocean currents that have flowed in the same patterns for centuries are shifting as the planet warms. Underwater landscapes that have been stable for thousands of years are changing as sea levels rise and currents shift. Features that were mapped just a decade ago might look completely different today. Scientists are discovering that they need to remap areas they thought they already understood. The ocean floor isn't static. It's a dynamic, changing environment that requires constant monitoring and updating. This is adding even more urgency to the 2030 deadline. It's not enough to map the ocean once. They need to create mapping systems that can continuously monitor and update their understanding of the seafloor. But perhaps the most urgent aspect of this race against time is the simple fact that we're running out of time to make decisions about our planet's future. Climate change, ocean acidification, rising sea levels, changing currents, these are challenges that require immediate action based on the best possible understanding of how ocean systems work. But we can't make good decisions about ocean management with incomplete information. We can't protect marine ecosystems we don't understand. We can't prepare for sea level rise without knowing exactly how ocean currents and seafloor topography will interact as temperatures change. The 2030 deadline isn't arbitrary. It's the last realistic opportunity to gather the information we need to make informed decisions about our planet's future. And despite all the challenges, despite the incredible scale of the task, despite the urgency of the timeline, the scientists working on this project are optimistic. They're optimistic because the technology is advancing faster than anyone expected. Mapping systems that were science fiction just a decade ago are now routine tools. Artificial intelligence systems are processing data at speeds that seemed impossible just a few years ago. They're optimistic because the level of international cooperation on this project is unprecedented. Countries that disagree on almost everything else are sharing data, resources, and expertise to achieve this common goal. They're optimistic because the financial support is real and substantial. The Nippon Foundation's $185 million is just the beginning. GIP, governments, corporations, and other organizations around the world are contributing additional funding and resources. But most of all, they're optimistic because they understand what's at stake. This isn't just a mapping project. It's humanity's final chance to completely understand the planet we call home before it changes beyond recognition, and they're going to make it happen. And when they do, when that last square mile of ocean floor is finally mapped, when the last underwater mountain is charted, when the final deep-sea trench is surveyed, we will cross a threshold that no species in the history of Earth has ever crossed before. We will know our planet completely. Think about that for a moment. For the entire 4.5 billion year history of Earth, the vast majority of the planet's surface has remained unknown. Even when life first evolved in the oceans, even when it spread to every corner of the seas, no single species ever understood the complete geography of their world. Dinosaurs lived on Earth for 165 million years, but they never knew what lay beneath the waves. Early humans evolved alongside the ocean, used it for food and transportation, but never glimpsed the underwater mountain ranges and deep-sea valleys that covered most of their planet. Even today, as we send spacecraft to other worlds and dream of colonizing Mars, we remain strangers to most of our own planet. But that's about to change. Picture a child born in 2035, just a few years after the Great Ocean Mapping Project is complete. For that child, the concept of unknown ocean will be as foreign as unexplored continents is to us today. They'll grow up with perfect three-dimensional maps of every underwater mountain range, every deep-sea valley, every coral reef, every hydrothermal vent on the planet. They'll study ocean currents and marine ecosystems with a completeness of understanding that no previous generation could imagine. To them, the ocean won't be a mysterious, unknowable realm. It will be as familiar and well understood as the continents their parents grew up learning about in school. But complete ocean mapping will do more than just satisfy scientific curiosity. It will birth entirely new fields of science, new industries, and new dreams. Imagine marine archaeology becoming as sophisticated as land-based archaeology, with detailed maps guiding researchers to shipwrecks and submerged settlements with pinpoint accuracy. Picture deep-sea mining operations that can extract rare earth elements with surgical precision, leaving delicate ecosystems undisturbed. Envision underwater cities built with perfect knowledge of seafloor geology and ocean currents. The economic implications alone are staggering. Industries that don't even exist today will emerge from our complete understanding of the ocean floor. New forms of renewable energy that harness deep-sea currents. Pharmaceutical discoveries from previously unknown deep-sea organisms. Revolutionary materials science based on the unique properties of minerals formed in extreme deep-sea environments. But perhaps the most profound change will be in how we see ourselves as a species. Throughout human history, we've defined ourselves as explorers. We've crossed continents, climbed mountains, sailed across oceans, and ventured into space, always driven by the fundamental human need to know what lies beyond the horizon. When the last ocean trench is mapped, we will have reached every corner of our planet. There will be no more unknown territories on Earth, no more blank spaces on our maps, no more mysterious realms where anything might be possible. This moment will mark the end of the age of exploration on Earth and the beginning of something entirely new, the age of complete planetary knowledge. And what a foundation that knowledge will provide for everything that comes next. When we finally venture to other worlds, and we will venture to other worlds, we'll do so with the complete understanding of how planets work that comes from knowing every detail of our own world. We'll understand the relationship between seafloor topography and climate, between ocean currents and weather patterns, between geological processes and the evolution of life. That knowledge will guide us as we explore the subsurface oceans of Europa and Enceladus. It will help us understand what to look for when we search for life on planets orbiting distant stars. It will inform our decisions about how to terraform other worlds or build sustainable colonies on alien landscapes. Complete ocean mapping isn't just about Earth. It's about preparing for humanity's future among the stars. But even before we reach other worlds, complete ocean mapping will transform our relationship with our own planet in ways that are difficult to imagine. Weather prediction will become so accurate that we'll plan our lives around forecasts that extend months into the future. Natural disaster preparation will evolve from reactive emergency response to proactive precision planning. Resource management will be based on complete inventories of everything our planet has to offer. We'll move from being a species that lives on Earth to being a species that truly understands Earth. And this transformation is happening remarkably quickly. Consider the pace of progress in ocean mapping over the past few decades. In 1970, we had rough maps of maybe 5% of the ocean floor. By 2000, we had basic coverage of about 15%. Today, we're approaching 30% with increasingly detailed resolution. At this rate of progress, the children who are born today will witness the completion of the greatest mapping project in the history of any species on any planet. They'll live through the transition from the age of the unknown ocean to the age of complete planetary knowledge. But this transition isn't just about completing a map, it's about completing our understanding of what it means to be human. Throughout our history, we've been defined by our relationship with the unknown. We've been explorers, adventurers, seekers of new frontiers. Our greatest achievements have come from pushing beyond the boundaries of the known world. What happens when there are no more boundaries to push beyond? What happens when the last frontier on Earth has been crossed? I believe something beautiful happens. I believe we evolve from being explorers of our world to being stewards of our world. Instead of seeking new territories to discover, we'll focus on understanding and protecting the territories we've already found. Instead of racing to map unknown regions, we'll work to preserve and restore the ecosystems we've identified. Complete ocean mapping will mark the moment when humanity transitions from the exploration phase of our relationship with Earth to the stewardship phase, and that stewardship will be informed by the most complete understanding of a planet that any species has ever possessed. We'll know where every fragile ecosystem exists and how to protect it. We'll understand how every current flows and how changes in one part of the ocean affect weather patterns around the globe. We'll have identified every resource our planet offers and be able to use them sustainably. For the first time in human history, we'll be able to make decisions about our planet based on complete information. But perhaps the most profound impact of complete ocean mapping will be psychological. Humans are meaning-making creatures. We understand ourselves through stories about who we are and where we come from. And one of our most fundamental stories is that we live on a mysterious planet full of unknown wonders. What happens to that story when the mystery is solved? I think it evolves into something even more beautiful. Instead of being mysterious, Earth becomes knowable. Instead of being unknowable, it becomes understood. Instead of being alien, it becomes home in the deepest sense of the word. We'll know our planet the way we know a beloved neighborhood. Every street, every building, every hidden corner. We'll understand its moods and rhythms, its patterns and cycles, its strengths and vulnerabilities. And from that complete knowledge will come a kind of love and connection that's impossible when something remains mysterious and unknown. Think about the people you love most in your life. You don't love them because they're mysterious. You love them because you know them completely. You understand their quirks and habits, their fears and dreams, their strengths and weaknesses. Complete ocean mapping will allow humanity to know Earth in that same intimate, comprehensive way, and from that knowledge will come the wisdom to be the kind of planetary stewards our world deserves. We're living through the final chapter of the age of exploration on Earth. Within our lifetimes, possibly within the next decade, humans will have visited every corner of our planet, mapped every landscape, charted every ocean current. The age of the unknown ocean is ending. The age of complete planetary knowledge is beginning. And at the center of that transformation is the simple, profound act of mapping the seafloor. It's a project that connects us to the greatest explorers in human history, the Phoenicians who first ventured beyond the sight of land, Columbus who sailed toward an unknown horizon, the crew of HMS Challenger who dropped the first scientific instruments into the deep ocean. But it's also a project that will define the future of our species for generations to come. Because once we know our planet completely, once we understand every ocean current and every underwater mountain range, once we've charted every square mile of the 71% of Earth that remains hidden beneath the waves, we will have achieved something unprecedented in the history of life itself. We will have completed the map of our world, and then, finally, we'll know what it truly means to live on a water planet spinning through the vast cosmos. We'll be home.